Do you have it, Bob?
Yep, I found it. Let's see what this is. All right. What's up now? Oh, Al is supposed to be in this class and he's asking me questions. Al, now's not the best time. All right. Anybody having trouble hearing me?
Oh, you're good.
All right, let's do this thing. Some PowerPoint features will be dropped. No, it's not working. Now, why can't I get this to go streamline? All right, who knows how I can select, watch this. Oh, that's the answer. There we go. All right, can you all see this now? Is this okay? Baron, I'm going to pick on you since you.
Yes, it is.
You got it.
All right, team. I show 42 participants. It's a little after 7 o'clock, so we are going to proceed now. This is Chapter 3. Welcome, everyone. Thank you for being here. We're going to discuss moisture, latent heat, fog, and stability. This is starting to get into some of the taller weeds now in terms of some of the science stuff, so hang with me. This is this chapter. It's composition of the atmosphere, the dry and with water vapor, the vertical structure of the atmosphere, the troposphere, stratosphere, mesosphere, thermosphere, a definition of what is lapse rate, the adiabatic process, and the related lapse rates. There's the dry adiabatic lapse rate and then the wet adiabatic lapse rate. We're going to talk about those very shortly. Properties of water, phases of water and change among them, and then latent heat of phase changes. So a lot of energy involved there. And we are going to be referring to your study manuals. So I don't know if you can look at your study manual and watch these slides. Most of you hopefully have had a chance to look over all the materials, so this will be just going over it verbally. The overview continued. How moisture in the atmosphere is reported in terms of absolute humidity, relative humidity, and the dew point. Fog types. Here's where it gets back to more relaxing. Formation and dissipation. Atmospheric stability. That's something that won't be quite as difficult. Absolute and conditional stability. And then we're going to talk about absolute instability. And an example of the Chinook or the phone wind. I don't know how to pronounce phone. I think it's phone. Let's talk about the Earth's atmosphere. What makes up the air around us? The major constituents are nitrogen and oxygen. From the graph, you can see it's 78% nitrogen and 21% oxygen. And then the last 1% are different things such as carbon dioxide, neon, helium, and methane. But mostly it's argon in that last 1%. So as it says there, the rest is mostly argon with small amounts of carbon dioxide, neon, helium, and methane. And there is a variable amount of water vapor. And water vapor actually is the inspiration for a lot of the changes in weather we see, the amount of water vapor or the dryness of the air. Here's the structure of the atmosphere. So if you can all see here, the atmosphere has 4 major layers and 3 boundaries. The primary distinguishing feature is the temperature change with height, and most of the water and most of the weather occurs in the troposphere, which is the lower layer. So if you look down here, you're down in the troposphere. As you go to a higher altitude, the temperature, and this is for basic understanding, it decreases with altitude. Once you get up around the tropopause, and you get up into the stratosphere, the temperature actually rises again with altitude until you get to the stratopause. And up in the mesosphere, which is you have the stratosphere and the thermosphere, in between in the middle sphere, the mesosphere, where again, just like in our troposphere, the temperature decreases with climbing altitude. And now you get out here in outer space, and the temperature, again, with height, it goes from warm to cold as you get it up into outer space. So this is right, the thermosphere is right on the outside part of our atmosphere. And you can see this depicts it, it's about 87 miles above us. And so these are the four things, the four different parts of the atmosphere you need to be familiar with. Remember the troposphere, as you get higher, the air cools. And I know I went backwards. So up here, it actually warms as you get farther to outer space. So the coldest point would be the top of the mesosphere, which is the mesopause. And it shows how cold it is up there at about -100, and that's centigrade. So the temperature change with height, you get further into outer space, it gets a little warmer, but it's a good idea to be in your spacesuit if you're up that high. Lapse rates. The way the temperature decreases or increases with altitude in the atmosphere is called the lapse rate. And this is where it starts to get into some of the more challenging theoretical stuff with math. And so we're going to talk a lot about lapse rate. The environmental lapse rate is what is seen at any given time and place and changes with altitude. Those shown on the previous slide are averages. In mid-latitudes, it averages about a loss of 3.5 degrees Fahrenheit per 1,000 feet. That's in the lower troposphere. And that's assuming it's fairly moist there. So minus 3.5 degrees Fahrenheit for every 1,000 feet. So let's say the temperature was 20 degrees here at the surface and you're at sea level. If you went up 2,000 feet, it'd be 2 times 3.5 or subtract 7 for that number. And so it cools as you climb. So the dry adiabatic lapse rate is how fast unsaturated air cools as it is pushed up. Its nominal value is a loss of minus 5.5 degrees Fahrenheit per 1,000 feet. You notice that they talked about the environmental lapse rate. Well, that's not as much of a lapse rate as if the air was dry. The dry adiabatic lifting rate, if the air is still dry, you haven't formed clouds yet, and the air climbs, it'll cool faster. The wet adiabatic lapse rate is how fast saturated air cools as it is pushed up, as it is forced higher in the atmosphere. So its nominal value is about minus 3.2 degrees Fahrenheit per 1,000 feet. So once those clouds get to a certain altitude, or once that air gets to a certain altitude, it forms clouds. Now, after it forms the clouds, it'll still cool as it climbs. It just doesn't cool as fast. So below that point where it's saturated, it's nominally a loss of 5.5 degrees per Fahrenheit, 5.5 degrees Fahrenheit per 1,000 feet. Once you have clouds, it'll still cool as it climbs. It just doesn't cool as fast. So the reason that for the difference between dry and wet rates is shown later in this chapter. So the word adiabatic, what does adiabatic mean? So we're going to, I guess, talk more about lapse rates. Yeah, the adiabatic process. So more about lapse rates. The average environmental lapse rate is shown on the top figure. The air in that case is not rising. So an adiabatic lapse rate, they're named for the adiabatic process. What is the adiabatic process? Well, it's very much a scientific explanation where adiabatic processes occur without the addition or loss of energy to or from the outside. So it's almost like a test tube that nothing is impacting it. You're not cooling it, you're not warming it. It's just in a theoretical, perfect standard atmosphere as you would raise that parcel of air and not have any outside additions or subtractions of energy from that. So you're going to see that word again, and that's a good word to have kind of committed to memory. It's a process where nothing adds or subtracts energy from the outside. So air rising cools adiabatically. Air sinking warms adiabatically. So in other words, it increases in temperature. So over here you can see your theoretical air parcel. And here it is at the ground. It's at 30 degrees Celsius. That's a pretty warm day. Those of you guys know what 30 degrees Celsius, that's pretty toasty. So that air rises, and as it rises, this parcel of air expands and it cools. So in this case, if you were to take it up to this temperature, you notice that the volume is greater. And if it was to continue to rise, it would expand even more and cool even more. As it descends, it would be compressing and the air parcel would actually warm up. So it would go 10 degrees Celsius to 20 degrees Celsius. And if that same air parcel were to continue to sink, it would warm up to 30 degrees Celsius just as when it climbed, assuming there's no gain or loss of energy within it. And that's a theoretical process. The wind is going to blow, heat is going to be added or cooled, so this is very theoretical, but it helps us understand what happens with the energy of the atmosphere. So now we get into talking about the properties of water. So water is an amazing thing. The properties of water are uniquely suited to life. So water, instead of shrinking when it freezes, it expands when frozen, making ice float on top of lakes and rivers. It changes phase at temperatures found on Earth, and it's an excellent solvent. So water can wash things away and clean things up. So the properties of water, its properties are also well suited to weather processes because it releases a lot of energy when it condenses or freezes. It actually releases more when it condenses than when it freezes, but it still releases some heat when it freezes. So water is an efficient absorber of infrared energy. You're going to see this again. So the sun's light, it is an effective absorber of infrared energy. It can transport energy from one location to another as the air moves around or advects. And there's, at this time, an abundant supply of water on the planet. More properties of water. So the amount of water vapor in air by weight varies. Some places, like in the desert, you could have less than 1% of the atmosphere would actually be water vapor. Where in other places, like Alabama or somewhere along the Gulf, you can have up to 4% of very moist air. And so even in a very humid environment, the water vapor amount in air would only be about 4%, but that's a pretty humid day. Moist air is lighter than dry air. Now this is kind of hard to understand. Now how come air with water molecules in it, how can that be lighter than just dry air? And the reason is nitrogen, which makes up most of the air, it's 79% roughly, 78, 79%, has a molecular weight of 28. The molecules of oxygen, which is O2, it's not just O, it's O2, has a molecular weight of 32. Because floating around, we don't have just straight up oxygen, we have O2 molecules. And then the argon, which is less than 1%, has a molecular weight of 14, so it's also very light. So here, of all these things that are already in the atmosphere, the average molecular weight is 28.7 molecular weight. This is pretty small. Molecules are small. However, water with hydrogen, H2, and two molecules of hydrogen paired up with one molecule of oxygen has a molecular weight of 18. So even though it's heavier than argon, most of the atmosphere here is made up of nitrogen and oxygen. So water vapor is lighter than most of the other molecules that make up our air. So every molecule of air replaced by one of water lowers the weight of the air by 10.7 grams for every 18 grams of water. So you can see if you add water to a parcel of dry air, you'll make it lighter. So that causes it to rise. So it can cause it to rise because it's lighter than the air around it. So phase changes and latent heat. Let's talk about latent heat. The phases of water are shown below, along with the names of the phase change processes. This is an important graph to understand. It's pretty challenging. So while water melts or evaporates, it stores large amounts of energy called latent heat. So if something to go from ice directly to water vapor, that's something called sublimation. So it doesn't turn into water and then turn into water vapor. It goes straight from ice into water vapor. That's sublimation. And if something goes straight from water vapor into rock hard ice, that's deposition. Deposit some ice on your windshield when you're driving in the airplane, maybe. So those are a couple of interesting words. But normally we think about ice melting, and in order to get ice to melt, you have to add heat to it. You have to make it warmer, and it takes about, for a quantity of ice, it takes 80 calories of latent heat to turn that into water. So it takes in heat. And then if it's water, and you like a pot on the stove. Let's say there was a pot on the stove and you're making tea or boiling water for an egg or something like that. In order to get that water so hot that it boils and the water on the top starts to evaporate, you would have to add 504 calories of latent heat to vaporize it. So you notice there is amount of heat that's added to ice to turn it into water, but there's a lot more calories of latent heat that have to be added to get it to turn into water vapor, which is why, by the same token, if you have water vapor that now cools and condenses, as it cools, it releases latent heat, and it releases a lot of it, 540 calories, in order for it to go from water vapor to water. So as those clouds rise and they cool, and that causes the condensation, now you have heat released inside there, which is why we can get some spectacular thunderstorms because of the released latent heat. And up here in Illinois today, and then up in Wisconsin for you Wisconsin folks, if you turn water into ice, it freezes. And as it goes from water to a solid ice, you also have a release of heat. So that is also 80 calories per gram. So if you look up here, you can see that in order to go from ice to water vapor, it has to add this amount of calories. You would have to warm it by that amount, and you would have to add this amount. So it's 540 plus 80 to get it to go from ice all the way to water vapor. So per gram, that's 620 calories. And by the same token, if you would have water vapor somehow go straight from water vapor to ice, it would take the 540 calories that it would normally go to water, and you have to add on the 80 calories that it would take in this step. So 540 calories plus 80 calories, that's 620 calories per gram of water that is released when something goes from water vapor to ice. So this is pretty complicated stuff, but you can see that there is a lot of latent heat involved, which is why once you have water vapor going into just water, changing from a gas to a liquid, there's a lot of heat that gets released for every gram of water that is created. So that's a lot of energy, which is why we get thunderstorms and hurricanes and stuff like that. So the importance of latent heat. The latent heat tied up in water, which is 80 calories per gram, and the even larger amounts added in water vapor, 504 calories per gram, is carried with the water or vapor as it is transported in the atmosphere. So as that mass of air moves around, if it's a moist mass of air, it's got a lot of energy in it. So if you have pretty, quiet weather and you have some moist air come into the area, you can have the weather change rapidly, and you can have a lot more energy coming in with that mass of air. So this transport of latent heat is added to conduction, which is where the air is touching the ground as it passes overhead. It's added to convection, where the air rises, and radiation, from the sun coming down mostly, and some bouncing off the surface of the earth and back up into the atmosphere as a means of energy transport. The condensation of water is a key driver of many kinds of weather phenomena, such as thunderstorms and hurricanes, because the released latent heat upon condensation provides energy to the systems. Let's talk about humidity now. What do we care about humidity? The concentration of water vapor in the atmosphere is reported in three primary ways. So this is a discussion of what is humidity. Absolute humidity is the mass of water vapor in any given mass of air, normally given as grams per kilogram of dry air. So the mass of air can hold increases with increasing temperature. So the further north, there's less humidity because the air is cooler, but you go down south, now the air can hold increases, more water vapor as the temperature increases if you go someplace warmer. Relative humidity. Relative humidity is a ratio of the mass of water vapor in the air to the maximum it can hold at that temperature. So usually we talk about that as a percent. How humid is it? If it's 100% humid, you're going to have fog, or you're inside a cloud. All right, then we're going to talk about the dew point. The dew point is the temperature the air would have to be cooled to in order to reach saturation. This is not real good grammar here, but you understand the idea. If the air is cooled to a certain temperature to the dew point, boom, you have fog or you have a cloud. A fourth seen occasionally is the dew point depression, and that's the temperature minus the dew point. So if you're at 100% humidity, the temperature minus the dew point would be 0, right? Because you're at 100% humidity. There's no difference. And so if you had a big difference in very dry air, that's going to be a large number, the distance between the temperature and the dew point. So humidity can be measured by an instrument called a psychrometer. So here you see, as you start up here in Chicago, where it's colder than 30 right now, and then you go down to someplace south of where you guys are in Florida, where the temperature is 95. This is what would depict 100% humidity. So here, your grams per kilogram is less than 5. So how much moisture can you have in the air? Less than 1 gram of moisture per kilogram of air. But as the air is warmed, it expands so that now you can have much more grams per kilogram of air. So that for 100% humidity, that means you can have many times, 6 times or 7 times or more the amount of water vapor in the air as you get further south and it's warmer. So here's your theoretical parcel of air, and you're somewhere, in Kansas, and the air is pretty warm. It's a summer day. It's up mid 80s. Well, what happens at night when the air cools? Well, as the air cools, this same air parcel will now get closer to the dew point. And when it gets to the dew point, you can reach 100% relative humidity. And you could start to see condensation. You could see fog.
Bob?
Go ahead, Jeff.
In the book, it said hygrometer. Are there 2 types of devices?
What's that, the hygrometer?
It said hydrometer in the book, but on the slide, it said psychrometer or something like that.
Right. Yeah, they both measure humidity.
Okay.
Yeah, it's interesting. It does say hygrometer. These slides are pretty new, so I would go with the slides, but I think both words mean the same time. So here you can see the temperature is cool to the dew point, and that's an indication that the dew point here, it was at 83 degrees. The dew point was all the way down here at 53. And when the temperature cooled from the 80s all the way down to the 50s, that's when you reach that 100% humidity mark and you would perhaps get fog. So here's a scenario. It's a 3-day plot, a theoretical 3 days here. And right in the beginning, the temperature and the dew point were very close. So the red is the temperature, and the dark green here is the dew point. Now, because they're very close, that means that the relative humidity was very high. There's a very small difference here between the temperature and the dew point. Now, as the temperature goes up here and the dew point gets to a certain spot and kind of plateaus, now overall there's a bigger distance between them, so the relative humidity is less. That makes sense? And so in here you had a very high relative humidity, and you get out here as some dry air comes in, and you can see the temperature goes down a little bit here on the, and here is, let's see, the first day, that's midday, no, midnight, 3 a.m., 6 a.m., noon, okay. So here it's midnight at the start of our story where the humidity is high. Then at noon, the air starts to warm a little bit so that the temperature increases. So by 9 o'clock in the evening, you're starting to see a spread here so that you can see the blue line here goes down with the relative humidity decreasing. So you you should be able to sort of see a relation here. As the temperature decreases, the air temperature and the dew point get a little closer together, which causes a little spike here in relative humidity after midnight, early in the morning on the second day. But as this day goes on, the air dries out, and so the dew point lowers, and the sunshine comes out, and it heats up around noon. So now there's a big difference between the temperature and the dew point, and that means the relative humidity is less than 10%. It's pretty low. But later on that night after midnight, the air cools, the air gets a little more moist, so there's a shrinkage in the distance between the temperature and the dew point. Now you have the relative humidity go back up over 70% here. I don't know if you can see the percentage right here. And good. Does everybody see kind of the relationship there? I hope that kind of makes sense. 47. Very good. Now we're going to talk more about that station model. This was a big topic the first night, which I sent out an email. I hope that kind of explained things a little better about the station model. So here's a typical National Weather Service station model. And from here, you can see down here is the dew point. So this station model adds the dew point temperature in degrees Fahrenheit. So this isn't centigrade, it's Fahrenheit. So the temperature here is 67. The dew point it shows is 59. So the dew point depression is 8 degrees less than the actual temperature. So dew point depression is 8 degrees Fahrenheit. So the relative humidity is about 75% as indicated by that last graph. So we're going to go back and look at that. Remember 67 and 59. 67, and the dew point was 59. So you can see here the distance between these two is about 75%. So that's just estimating. All right, we got out of the woods there with latent heat. It is complicated. You don't understand it the first time, go read it again. The release of latent heat, once it starts firing those thunderstorms, that just gets things rocking and rolling in terms of the energy that is released when the storm is building. Now we get to talk about fog. So this is nice little break. The principles in this chapter help us understand fog. So fog forms in many ways, and it can last for hours or even days. Fog forms by either a decrease in the temperature or the addition of moisture. So you got an outside player here, which is more moisture is being added to the mix, and that can raise the dew point. So here's your basic types of fog that we're going to talk about. You have radiation fog, which happens when the temperature decreases. Advection fog, where you have colder air moving in. This also causes a temperature decrease. Remember the two things that can cause fog: addition of moisture, decrease in temperature. Here, precipitation fog, like when it's raining, that adds more moisture to the air, and that can cause fog. Or in the case where you're near a large body of water, steam fog, some people call it steam smoke, and that changes the atmosphere that you're in, or the type of air that you're in. So moisture is added there. Like in the Northwest, sometimes you get fog coming in from the Pacific. A couple other kind of unique types of fog. One is called upslope fog, and that's as the air climbs up the hill, the temperature cools, and that causes the dew point temperature spread to reduce, and you can get fog going upstream. And we're going to talk about valley fog, which is very similar to radiation fog, but down in a valley you don't get, the wind can be prevented from getting in there, so it can last for a while. So radiation fog, air near the ground cools to the dew point. This is probably the most common type of fog that we'll be familiar with here. The air near the ground cools to the dew point, the water condenses. So number one, it's a clear night. The winds are less than 5 miles per hour, so they're pretty light, not a lot of wind. So the heat is cooling after dark. The heat radiates away from the ground, which causes the ground and the air right next to us, right, where they conduct because they're touching each other, the air right next to it and the ground to cool. So heavier, colder air flows into low places, and fog forms as the air cools to its dew point. Fog is usually less than a couple of 100 feet deep. As the sun comes up the next morning, the temperature goes back up again. Its heat raises the temperature above the dew point, and the fog, we call it burning off. And now, I think that's probably a fair, people say, well, there's no fire, there's nothing going to burn. But the sun's rays are the radiation that's causing the fog to lift because it's warming the ground. And other times, if you could have a clear night, but if there was a clear night but the winds are blowing, strong winds prevent fog by mixing the air near the ground with warmer air that's higher up. So it keeps it from cooling. So it adds that heat to keep the temperature dew point spread from getting too close. Advection fog. What's advection fog? Advection fog is warm air moving over a cool surface, and it lowers the temperature. So here you have some warm air that's over land, and the wind blows it out over the sea, and that cools that air, which had a higher dew point. So now it's cooled down to its saturation point. So the moisture condenses. Wind pushes warm, humid air inland in the winter, which we call advection. When you're moving a parcel of air, moving it from one place to another, we're vectoring it, or advection. That's advection, when you're moving air. So that refers to air moving horizontally. 2, as the air blows over cold ground, or in this case, cold water, such as a cold current area, it cools to the dew point and that fog forms. So sometimes you'll have that on the East Coast when the warm air blows over the cold ocean. Advection fog can cover wide areas of the central U.S. in winter, causing airports or over cold water in the lee of warm air coming from land in the spring. So that's where you have a parcel of air moving, and that air goes over a cool surface, and as it cools, it creates fog. I'm going to look real quick, see if anybody has any important thing that I need to know. Ken, you told me that. Thanks, Ken. All right. Hopefully nothing else. All right. Thanks, man. Good. Where were we? Steam fog. What's steam fog or sea smoke? Well, water evaporates, raising the dew point temperature. So the sea, you have the sun hit it. It causes that energy adds to the water in the sea. That warms it, so the water starts evaporating. So number one, cold air blows over much warmer water. As the water evaporates into that cold water, it increases the amount, the dew point higher. So it increases that to the dew point. So once that number 3 vapor condenses into tiny droplets, on fall days you might see steam fog rising from ponds and streams as fog forms a foot or two above the water. It looks kind of like a flat plate. So that's what you could call steam fog or sea smoke. How do you get upslope fog, like over in the Rockies on the west coast of the U.S.? The air is raised orographically. What does that mean, orographically? Well, that means it goes from low terrain to higher terrain, or orographic lifting. You probably don't use this every day, that word, but it refers to rising terrain. Or orographic lifting is rising terrain. So that air gets cooled to the dew point, and as the wind blows humid air, as the wind is blowing humid air up in the hills or mountains, as the air rises, it cools to the dew point, and now you've got fog drifting up the hill. So that's widespread upslope fog is common on the Great Plains where the land slopes gently upward towards the Rockies. So if you've been out west, you may have seen this before. You may have seen pictures of it, but orographic lifting can cause upslope fog. Finally, what's valley fog? You see this in the Smoky Mountains, you know, where my dad grew up. Number one in the steppe, in valleys, especially in the west during the winter, radiation fog can become more than 1,500 feet thick. So weak winter sun isn't strong enough to evaporate the fog completely, but it might warm the ground enough for a layer of fog up to 500 feet above the ground to evaporate. Such fog can last for days until the storm comes along or strong winds push out the cold air. So it's kind of like fuel vapors in the bottom of a boat. You know, you get that moist air and it just kind of hides down there in the valley. And unless there's a storm to wash it out or cold air comes in or the wind blows through there, it just sits down there like smog in LA or something like that. So this is a kind of fog, valley fog, that can last for days. We talked about the radiation fog back here, and we talked about the fact that once the sun comes up, it can go away fairly quickly. All right, I'm going to have someone, I'm going to pick on people. I hope you guys enjoy this. I'm picking on you. Linda, can you read for me? This is the type of fog. Linda, read from here down and tell me about a typical occurrence, winds, and dissipation.
Just read the boxes.
Yeah, read the boxes from here on down. So it typically occurs, clear night, winds, how many knots, dissipates, blah, blah, blah.
Okay. Clear night with radiational cooling in low wet areas. Typical winds 3 to 5 knots for gentle mixing. Dissipation, daytime warming of ground warms air through conduction and mixing.
Good. That was radiation fog. Mario, what can you tell us about valley fog? Did you see what Linda did there? Do the same thing. Typical occurrence, winds, dissipation.
Okay, then usually during winter and valley with radiational cooling, the wind is between 3 to 5 knots, gentle and mixing. The dissipation is a blend of storm with strong winds that replace saturated air with dry air.
Excellent. Good. And Mark, Frankel, tell us about advection fog. So Mark, can you answer, Mark? Or are you driving? I'm trying to remember. Are you driving, Mark?
Sorry about that. I thought
No
you
worries.
could hear me. So warm moist air is transported over colder surface. The winds are 4 to 15 knots, and the dissipation is wind changes direction to warm air flow is eliminated. Sometimes higher winds lift off the ground.
Good. That's all advection fog. Hazem, are you here? Mark, you here?
Yep.
Mark, what can you tell us about upslope fog? When does it typically occur? How about the winds and dissipation?
Typically occurs in warm, moist air lifted by upslope air flow, cooled by expansion to saturation. Winds is sufficient for lifting and dissipates in daytime warming. When it evaporates, fog or wind may change direction.
Excellent. That's upslope fog. Mike Haley, what can you tell us about precipitation fog? Yeah, Mike?
Precipitation fog, typical occurrence, rain from warm air falling through colder air at surface, saturates cold air at the surface. The winds aren't important, and the dissipation, frontal passage or end of participation or precipitation.
Precipitation, right on. Good. Mike Harvey, can you tell us about sea smoke? You hear Mike Harvey? I might not be plugged in today. Mike Zindrick. You hear Mike?
Yes.
Tell me about the typical occurrence of sea smoke. So when does a typical occurrence of sea smoke? Can you hear me okay, Michael Zendrick?
I'm breaking up here a bit. Just a second.
Sorry.
Sea smoke. Cold air blows over warm water, taking on moisture to saturation. Winds are 4 to 15 knots, and it dissipates daytime warming or wind changes direction.
Right, during the daytime. Good. All right, thank you, everyone. Let's talk briefly about dew point and frost. The dew point, when you have dew, it's above 32 degrees Fahrenheit, so it's not freezing cold. If the temperature and dew point are close together, you can have the creation of dew. Now, if it's colder than freezing and the air is humid enough, you can have frost develop here. And that's when the temperature is below 32 degrees and the air is so moist or humid that it goes straight from a gas to a solid, right? So it sublimates, sublimation, good. So that's a lot more energy as it goes from gas to solid, right? Good. Atmospheric stability. Let's talk about what makes the atmosphere stable or unstable. Atmospheric stability can have one of three states. The first is absolute stability. An air parcel lifted to any height, if it has stability, will just simply return down to its original position as it is heavier than the surrounding air. And you can see here it's below the environmental lapse rate. So as it rises, gets up here, and it just says, I want to go back home again. So it goes right back down again. So that's not a scenario where you have a lot of weather develop. So as this is more altitude, here's the warmer temperature, and it's not that warm. It's colder than the environmental lapse rate. And so as a result, it's stable. It has stability. So the second type of stability is absolute instability. An air parcel will rise on its own since it is lighter than the surrounding air and only stop when it reaches stable air, such as all the way up in the troposphere. So here, the air is already warmer than the environmental lapse rate. So it's at a higher temperature. So once it starts rising, it just keeps going, and nothing's going to stop it until it gets all the way to the tropopause. So that is some very unstable air. That's good for development of hurricanes or thunderstorms. You get out over, middle of the Atlantic, and the water's warm, and the air is the environmental lapse rate is low, and that air starts rising, and that's when you get them hurricanes forming. The third type is conditional stability. Now the book actually messes this up a little bit, but here, conditional stability, air is pushed up a little when it's stable, but as soon as it gets above that environmental lapse rate, boom, it just goes up like a rocket. So conditional stability is, at first it is stable, but then when it busts through this environmental lapse rate, it becomes warmer, and now it's just the cloud is going to develop. So up until this point, you won't have a cloud. Once it hits this point, boom, it rises, and here's where you're going to have the clouds. So the air is warmer, so it's right close to the environmental lapse rate, and it rises a little bit, but if it doesn't bust through this line, it's not going to start forming clouds. So it depends on, if you get a little lifting here, you won't get those clouds develop. But if it somehow gets pushed up through the environmental lapse rate up into this air where it's warmer, it'll just keep climbing. So what can change that stability? How did it get to such an unstable point? Atmospheric stability is constantly changing. Here's an example. It shows progression during the day. You get the morning, early in the morning. The top figure shows an early morning inversion with stable air. You don't have a lot of weather happening. It's a summer morning, maybe. There's a partial air just kind of floating around down here. It rises a little bit, but then it becomes heavier than the air around it, so it just sinks right down. So nothing really much is happening. Boom, in the bottom figure, the temperature has risen in the afternoon. The lower atmosphere is heated. Now you have instability. It's warm enough so that once that parcel of air starts to climb, it will continue to climb in the afternoon instability, and that's when you get those afternoon thunderstorms in summertime. So you can see here it's got the dry adiabatic lapse rate. It cools a little bit as it climbs, but it doesn't bust through the environmental lapse rate. Up here, it climbs a little bit, and it's already above the environmental lapse rate at the dry adiabatic lapse rate feature, and now it's going to create a thunderstorm or a rain shower. So what can cause an air to be pushed up or lifted? I don't know why they don't say lifted. In the old days, we said lifted. How is air pushed up? In the stability discussion, we talk about air being pushed up. How does that happen? We talked a little bit about the Rockies and the wind blowing up the Rockies, or graphic lifting, such as the wind blowing up the side of a mountain. And you can have it in, any parts of the world where you have rising terrain, East Coast, West Coast. Frontal wedging. Now, what is that? Well, when a front comes through, if you can, for those of you guys in Florida, what's a snowplow? But for here, you can imagine a snowplow pushing snow up into the air. And when a front comes through with that heavier air, the air in front of it will just get pushed up. It'll, just like a snowplow, it'll push it out of the way. And in this case, it'll start pushing it up. And that would be frontal wedging. Doesn't have anything to do with getting a wedgie like in gym class, where cold air pushes under the warm air, which would be like a cold front, or the warm air rides over the top of just cool air, maybe like a warm front. So another situation where you can have air lifted or pushed up would be surface convergence, where the surface winds come in from different directions, and as they meet, the air has no place to go, and so it climbs. So the air must rise because, you can't go down into the ground. It's not going to go away. Or you can have upper air divergence, which I like to think of this or explain this as sort of like a vacuum cleaner. You stick the vacuum cleaner over a bunch of marbles, they're going to, even though normally they wouldn't get sucked up, when you have the air peeling apart up high, it sucks the air directly underneath it up as it diverges, or as it splits in two different, like a fork in the road. I don't know if I explained that very good. A fork in the road. So the air below rises to replace that which is getting pulled out above it. So we'll see example of these in future chapters, but one example is shown on this next slide. So what's a Chinook? A Chinook is a warm wind on the lee side of mountains. So we were a few years ago, we were up in Bend, Idaho, and the temperature as it came down the backside of the mountains was like 114. It was hot. And we were pretty far north, all the way up there in Idaho. But a Chinook is a warm wind on the lee side, or the downwind side of mountains. So first the air is lifted orographically. Now as it rises here, clouds form, and it rises to the point where the water droplets condense, so rain falls out. So you have cooling as the raindrops fall out of the clouds, so the net cooling causes the air to cool off, and the rain occurs. Now the air, this parcel of air is not as dry as it was. It's drier than it was when it started its climb. So that same air that started this side of the mountain at 50 degrees is pushed up here. Moisture is lost, so you have net cooling. Now as it comes down the other side, it's drier air because that moisture got squeezed out of it, like squeezing a towel. So that warm, dry air, as it comes downhill, it heats. And notice it was 50 degrees over here. On the backside of the mountain, it's 80 degrees. It's much warmer. So it cools at the dry adiabatic lapse rate. And when it's saturated, it cools. When saturated, it cools at the wet adiabatic lapse rate. And on the backside, all it does is it comes down at the dry adiabatic lapse rate, which, if you remember from the beginning, we were talking about the rates. It's a lot bigger rate, that dry adiabatic lift rate. So it warms a lot more. So other places have us. Does anybody know what this word is? Phone? Is it phone in Europe? Has anybody ever been to Europe and heard that word before? We'll just teach them the word is Chinook. All right, a summary of this chapter. How are we doing time-wise? Really good. The atmosphere is primarily made up of nitrogen and oxygen, with small amounts of argon and other gases. There's a variable concentration of water vapor, which can be from 1 to 4%. The temperature profile varies with altitude in the 4 different layers. Try to remember all 4 layers. Obviously, you can remember the lowest one, which is the troposphere, and that's where we are, down here at the bottom. So the temperature decreases in the troposphere, but once it gets up to the top of the tropopause, it starts increasing again in the stratosphere. And the top of the stratosphere is the stratopause. And once you get into the stratopause, you see a change, so that up in the middle sphere, the mesosphere, the temperature starts decreasing with altitude until you get to the top of the mesosphere, which is the mesopause. And then after that, the temperature actually increases as you get into outer space. So it's coldest at the top of the mesopause there, right? All right, temperature change with height is called the lapse rate. So what's the environmental lapse rate? That's what's currently happening in the atmosphere. So it's not going to be the same because there's going to be some humidity, but it's probably not going to be totally humid. So a dry adiabatic lifting rate, the adiabatic lapse rate is how air cools when ascending or warms when descending. So it's a larger number. Water is a very important substance in the atmosphere. It changes its state at normal temperatures. It carries very large amounts of latent heat, and it is an efficient absorber of infrared energy. You're going to see this one again, so hopefully you remember that one there. Phases of water. Water can be solid, which would be ice, liquid, and gas, which would be water vapor. Ice and water, in between them, you either have melting or freezing. So here the latent heat is about 80 calories per gram. But when you get water switching back and forth to vapor, there's a lot more energy. So that's called evaporation or condensation, and that's 540 calories per gram. And then you get the extremes, which is water going directly into vapor or vice versa, and that would be called sublimation or deposition, like it could deposit ice on something. So that takes these two numbers combined, 620 calories per gram. So what's latent heat? It's energy needed to melt ice or evaporate water. So the release of this latent heat by condensation is a major driver of the atmospheric processes. Finally, in the summary, humidity is a measure of water vapor in the atmosphere. Absolute humidity is concentration of weight, so it's a number of grams of water per kilogram of dry air. Saturation absolute humidity is the maximum moisture air can hold at a temperature. Relative humidity is a ratio of absolute to saturation absolute humidity. The dew point is the temperature air must be cooled for saturation to occur. What's stability? Stability of the atmosphere is its tendency to rise. Absolute stability means the air, if lifted, will just return back to its original height. Conditional stability means air lifted far enough will continue to rise, but below that lapse rate, it'll just continue back down if it's not at the lifting rate there. Absolute instability means air will rise on its own. It's like in a warm afternoon in a summer day. Air can be lifted in 4 different ways. We talked about this. Orographic lifting, being pushed up the side of a mountain. Lifting is wind blowing up a mountain. Frontal wedging is cold air as you have one, like a cold front pushing up warm air as it moves in, or a cool front, which is coming in, that would be pushing up the air in front of it. Surface convergence, we have the wind coming together at the surface, forces air up, between the air between it to rise, and finally upper level divergence draws air upward. Remember we talked about it pulls apart like 2 jet streams splitting, and as those jet streams split, something has to replace that mass, and so the air underneath it rises. All right, I'm going to go around the room. Are you still driving, Adam, or can you answer a question? You there, Adam? He's probably driving. Let him keep driving. Let's see if you, Alejandro.
I'm here.
All right,
Sorry.
Adam. Can you see the screen?
I'm not the one driving.
Oh, okay. Sorry. All right. What is this? In the lower atmosphere, the temperature generally blank with altitude.
In the lower atmosphere, it normally goes down.
Decreases. Good. Alejandro, the troposphere is where most of the weather occurs because
contains most of the moisture.
Right on. Very good. Alex Carmichael, were you the one driving? The 2 most abundant gases in the atmosphere are? You there, Alex?
I'm here. What question number is that? 3?
Yeah, the third question is, what are the 2 most abundant gases in the atmosphere?
Temperature? Oh, no.
One you breathe.
Oxygen and nitrogen.
Correct. Next person is Anita Lutkus. A temperature increase with altitude is called what? Give her the hard question. You there, Anita? Can you answer?
I'll take a pass. I don't remember the word.
No worries. Amanda McAllister?
It's called an inversion.
Yep, correct. Good. Well done. Ann Brink, a warm, dry wind on the east side of the Rockies is called what? It's not the helicopter.
I can answer that one.
Is that you, Ann? You want to pass? You can pass. Ann? Arcia, are you here?
Chinook.
Chinook wind. Good. Next one is for Bill Vahey. I don't know if he's here. Bill, you here? When water vapor condenses, heat energy is? You here, Bill? Chris Strawman, when water vapor condenses, heat energy what?
It's released into the atmosphere.
Excellent. Don Broughton, the energy that is released when water freezes or vapor condenses is called? One of those new words we use. Don, you there?
Not sure I have this one.
No, it's for Don. Tom, it's for Don. Don. You there, Don? Thomas, you want to give it a guess? Go ahead, Thomas, if you know this one. Or you can guess.
Is called. I have it on the tip of my tongue.
That's all right. That's okay, Thomas. Deb Salvi, do you have this one? You there, Deb?
Yeah, I'm here.
One of those new scientific words we use tonight.
Sublimation.
No, not that complicated. Gary Cahill, you want to take a shot at this one?
I'll pass.
We found one to stump him. Are you here, Harold? Mr. Schlahan, paging Mr. Schlahan, are you here? One more try. Jane Bickle, any guesses?
Saturated.
What was it?
Saturated?
No. Jane Bickle, you want to take a shot at this one? The type of energy. Glad we did this. This is a trick one. It's latent heat.
Latent heat.
Good, Deb. How'd you know that one?
I was just thinking about it.
I was gonna. Jason Pfeffer, saturation can be accomplished by what two methods?
Sorry, Bob, I'm driving. And,
Oh, that's right. You're driving. Jeff Silberg, you keep driving safe over there. We need you, Jason. You
Yes,
drive
sir.
safe. Jeff?
Yes, sir.
Sure, it can be. You can add moisture to it, or you can cool it off.
Yep. Well done. Lowering the temperature, adding moisture. Well done. Jessica McAllister, the temperature at which water vapor begins to condense is called?
Dew point.
Dew point. Correct. Jim Davey, when the relative humidity of air is 100%, it is said to be?
Saturated.
Right on. Last page. John Puskar, a change in the temperature or density of air without the addition or release of heat energy is called? One of those scientific words that I used tonight. You got this one, John? This is a tough one. John Vondra, you got your book in front of you? You know this word? John Vondra?
I'm addicted to love.
What's that?
I just said I'm addicted to love. Sorry, I was thinking about a song.
Rodney. Kevin, do you know this one right off the top of your head? Kevin, you here with us?
I am, but I do not know.
All right, I'll give it to you. Adiabatic.
Adiabatic process.
Yeah, it's that new word that we threw in tonight. It's like a baseball bat. I die for a baseball bat. Adiabatic. So that's one of the new words we got in tonight. Larry Lindbergh, the term describing the tendency of lifted air to return to its former level is known as?
Absolute stability.
Absolutely. Good. Who didn't I pick on yet? Nick Nita, the term describing the tendency of air to rise on its own is?
think that's absolute instability.
It's not stable. It's instable. Good. Absolute instability. Very good. Pat Dugan, the term describing the tendency of air to continue to rise after being lifted to some higher level. So initially it's pushed up by something else, but then it continues to lift on its own is?
Conditional stability.
Conditional. I think it should be conditional instability. But this is the one I was talking about earlier. Yeah, it's conditional instability. Pat Leonardi, fog that forms at night under clear skies with little wind is called?
Radiation fog.
Good. All right, and I'm going to hop in here, and we are going to do, if I can figure out how to do this. All right.
Hey, Bob, real quick question.
Go ahead.
If I missed it, forgive me, but the question pattern has changed from the other night.
Well, we're going to get back into the normal pattern. So number one, Rodney, in the lower atmosphere, the temperature generally You there, Rodney?
Oh, yeah, I'm sorry. Go ahead.
You want me to answer that for you, Rodney?
Go ahead, Farron.
Charlie decreases with altitude.
Correct. Next one, Ron Briscoe. The tropopause is important in weather development since it?
Charlie, caps the development of convection activity.
Correct. Let's see. Who did I skip here? Paul Luna, number 3. One difference between the troposphere and the stratosphere is?
C, temperature distribution.
Very good. Number 4, Paula Wicks. The most abundant gases in the atmosphere are?
Oxygen and nitrogen. Let's see, that was B.
Number B. Very good. Penny Ross, number 5. The average environmental lapse rate in the lower atmosphere is? You there, Penny?
3.5.
I can hear you, Penny. There. Now you're not muted. Go ahead, Penny.
Negative 3 point. Did that work? Can you hear me? Sorry.
Yeah, I hear you good now. I think you accidentally remuted yourself. So what letter is it?
D, delta.
Delta is correct. Well done. Pete Lemire, number 6. The temperature increase with altitude in the lower atmosphere is called?
E, an inversion.
Very good. Now I got to get this to go away. How do I do that? Oh, there we go. Right on. Good job, Pete. Phil Leonard, a dry, warm wind descending the east side of the Rocky Mountains is a?
Chinook.
Very good. Correct. Reuben Howard, number 8. Water vapor is added to the air by?
Evaporation.
Excellent. Well done. Sean Landa, you here? Number 9. When water vapor condenses, heat is?
Released.
Excellent. Everybody get that? Well done. Sylvia, number 9. When water vapor condenses, heat is?
Released.
Oh, that's the same one over again. All right, I'll give you the next. Sorry, Sylvia. Number 10. The transition from ice to vapor without going through the liquid phase is called?
Sublimation.
Good. You guys might see that again. Next one, Tom Schildhouse, latent heat.
Latent heat is number B, released when water freezes.
B is in Bravo, right on. Number 12, Ken. Are you here, Ken? Saturation can be accomplished by? You there, Kenneth, or were you driving? I'm going to mute you, Rodney. Kenneth, you with us? Are you there, Ken?
Let's move on.
Oh, okay. I want to see if you're there. Adam, are you here?
Yeah, I'm here.
Number 12, saturation can be accomplished by?
C, Either A or B.
A or B. Yeah, this is one of the tougher questions. Good job. 13, Alejandro, the temperature at which water vapor begins to condense is called the?
The dew point.
The dew point. Good. 14, Alex Carmichael, if the water vapor content of an air parcel increases at constant temperature, the relative humidity blank and the dew point blank.
It's all of the above.
Not
No?
one of the choices.
Oh,
Alex.
I'm sorry, 14. Oh boy. Increases and increases.
Increases C. Good. Let's see. Amanda, how about 15? When air is saturated with water vapor. There, Amanda?
Yeah, just a second. Let's see. All of the above?
All the above is correct. Anita Lutkus, 16. Regarding the latent heat of fusion and the latent heat of vaporization of water.
C. Latent heat of evaporation is higher.
Correct. Ann Brink, back to you. 17. The term adiabatic means?
Give me 1 second while I pause.
Are you driving, Ann? Because I'm not going to have you answer a question if you're driving. You see you're driving?
Yeah, I'm driving. I was gonna look for a place to pull over.
No, don't. Sorry about that, Ann. My mistake. I should write down you're driving. Arcia?
Yes.
Number 17, the term adiabatic means?
A, no heat is added or subtracted.
Very good. Bill Vahey, I don't think you're here, are you?
Yeah, I'm here. I was just cockpit here earlier.
No worries. 18, the dry adiabatic lapse rate compared to the wet adiabatic lapse rate is?
Bravo, more negative.
Yeah, so watch out for the words here. It's not larger, it's more negative. That's a little tricky how they word that question. Thanks, Bill. Chris Strawman, number 19, the physical property or properties of water important to the weather is, or are?
I'm sorry, I have to unmute myself. It would be D delta, all of the above.
Very good, correct. Don Broughton, are you here? Number 20, the term describing the tendency of displaced air to return to its former level is?
Absolute stability?
Stable, very good. Next one is for Deb. 21, the term describing the tendency of air to rise on its own is? You there, Deb? Or did you say you were busy? I'm sorry.
Sorry about that, it was muted. A, absolute instability.
Yeah, it's not stable at all. Good. Gary Cahill, 22, the term describing the tendency of air to rise only after it has been initially raised to some higher level is? There, Gary?
Yeah, I'm here. Conditional stability.
Conditional, right. 23, Harold, fog that forms by adding moisture is?
C, precipitation fog.
Right on. Jane Bickle, 24, last one, fog that forms under clear skies at night is?
Radiation fog.
Radiation fog. Okay, does everybody need a quick pee break or a bathroom break or whatever you want to call it, break?
Yes.
All right, we'll be back here. I show about quarter after. We'll be back at 25 after. How's that sound? 25 after.
P.
Sounds good. Bob, I have a question.
Go ahead, Jeff.
So I'm having a hard time with the whole water vapor, and I understand the weight, the molecular weight. But the thing is, why doesn't water go up in the sky then? I don't understand. If water has a lower molecular weight, why doesn't Lake Michigan just like float over the air?
In solid or in liquid form, it's heavier than air. So that's why it stays below the air, because it's
Plus
not
the barometric
vapor.
pressure.
Well, when water condenses, you know, it's condensed into a liquid. It's heavier than the air, the atmosphere above it.
So its molecular weight is actually less, or it's because of the density of the molecule? Is it like there's more molecules?
Well, the density and the weight relate to each other, but yeah, it's heavier than the air above it. So liquids don't rise above.
Yeah, I
gas.
didn't think so. I just was like, how could adding water to the air make it lighter? But okay. But you're saying when it's in air format, then that's the idea.
Yeah, the vapor can rise.
Right.
How are you, Chaz? Are you there, Chaz?
I'm well. I am. I'm well, Bob. I was just going to tell Jeffrey that Lake Michigan is flying up into the air. We call it evaporation. It just doesn't all go up.
I see. Okay, good.
Bob, I have a technical
Go ahead,
question
Farron.
for you.
Sure, go ahead.
And that is, are you running a Windows or a Mac?
Windows, I think.
Would you consider enlarging the size of your pointer? I'm having a hard time on the graphics where you're trying to point out things following where your mouse is. It might just be me, in which case don't worry about it, but I'm trying to watch this with an eye to if I were leading a class, what would be some things that would make it easier to follow. So if you go to ease of access.
Where's that?
So in your search bar for, you know, to get into your programs, if you just type ease of access, like, do you want me to share my screen and show you?
No, just tell me if you can. Is it under settings?
So it would be down like by your little Windows icon. Yeah, settings. Yeah, right there, the search bar. Just type in ease of access. And then you should get like the
Always in this section.
your choices, and you should get something that says like control the size of your mouse.
Make the mouse easier to use? No.
I can't even, but it's so tiny on my screen, I can't see what your choices are.
Chaz, do you see what she's looking for on here?
Can you make your screen bigger?
Make the mouse bigger, Bob. Yeah, right there.
Adjust setting, yeah.
There you go. Yep.
Extra large.
You can pick bigger. You could make it a different color so it's easier to track.
So go to your extra large white, Bob, on bottom left if you like, or black, either one you like to use, and try that.
I wonder if I can do
Is that a little better? Is that better, Farron?
Well, like if you pull your slides up and then, see, it still seems pretty tiny to me. I'm not sure.
You might have had to hit OK.
Can you see it now? Because it's bigger.
It is a little bigger. I can see it a little better. Thank you.
All right.
I appreciate that.
No problem. How are you? Oh, Chaz, do you want me to, did you still have the code for the host key?
Yes, I do. I was able to find it.
Do you want to be the host then? Do you want to share your slides?
I always find that easier. Right now I'm trying to figure out how to close out this thing just barely enough to see if I can enlarge my pointer. I prefer to be my own host, yes, if I can.
All right, so I will stop sharing, and that will allow you to steal the sharing. How's that sound?
Okay, I guess, whatever we did yesterday, or Tuesday.
So let me know when do you have the code?
Yes, I do.
Do you remember how to do it? How to steal a host role? You go over participants, left click on participants, and then it should pop up on the right side.
Wait a minute. Participants, okay. Rename, no, I see. On the right side, you say.
Yeah, so go ahead and scroll over participants, left click on that, and way over on the right side of the screen should be a menu. You see a menu over on the right side of the screen? It has more.
No.
What?
Okay.
And then one of the more should be, oh, at the bottom right, it should say, next to mute all, it should say steal host or something like that. You see it over there?
No. Right side of the screen, all I've got is a line of people.
What was that, Chaz?
All I'm seeing is a lot of mute symbols.
All right, you left click.
I've got. Wait a minute. I hit share screen and I get host disabled participant screen sharing.
Well, if you stole the host job, then you wouldn't have to worry about it. But I'll just hit share screen and then you can share yours without having to be the host.
Okay, that's fine. That way you could ask the point. Now, how do I get rid of this thing? There we go. There, okay, there we go. Oh, dang it. This is going to take me a minute.
You want to know how to open the slides on the national website, or do you know that already?
No, I've got it. I've got them downloaded on mine. I know how to do that. Problem is I don't know how to squunch the.
Well, why don't I do it here? You want me to do it over here, Chaz?
I know what I want to do. I just can't figure out how. There we go. Wait a minute. And there we are.
I'm not seeing your screen. Did you click on share screen?
Go. We're getting there. We're getting there. That should do it.
Nice.
And you should be able to see.
All right, you look good, Chaz. I'm going to let you take over. Everybody should be back.
There it is.
Go ahead.
All right. Yeah, I don't have everybody's whole thing up. That's okay. I can't tell what I'm looking at. I hope everyone can see me. All right. Everybody here got back from the pee break?
Chaz, your camera's off.
Oh, is that? I know. Oh, well, we can't have that now, can we? There it is. There it is. There we go. And so there we are. Okay, now that I finally got to where we needed to be, only right on time. Okay, everybody back. Now, this is chapter 4, which I love to note that they call this sensible weather, meaning this is the intelligence stuff. This is what we've been working up to. All this, Bob is probably going to kill me for saying it, but all of the stuff we've been leading up to now comes down to this. What we're going to start talking about now are the things that actually cause the weather that we sense or know about or actually affect us. And the first thing that we need to talk about are air masses, the different types, where they come from, how they're modified, and how they become high and low pressure systems, which is what causes the weather, and how they move and what their characterizations are. Advance a little, Turkey. Oh, there we go. Okay, air masses. There are 5 different kinds of air masses. They are labeled by where they come from and what they're made up of. So they come from either continental sources or the ocean, maritime sources. They come from tropical or polar or Arctic. So you see the little box there, you've got basically 4 of them. 2 polar ones, 2 tropical ones, and at the same time, 2 continental ones and 2 maritime ones, each designated by those little letters. Plus, we've got the continental Arctic one, which is dry and very cold. And there they are. You see, the continental Arctic just sits over the North Pole, so it works on the weather, but we never see it, and aren't we lucky? We've got Maritime Polar, which is over the North Pacific, Maritime Polar over the North Atlantic, Continental Polar over northern Canada. This is the one that's driving us crazy right now. At least it's driving me crazy. I don't know about you. Then we have Maritime Tropical, which is over the Central Pacific Ocean, and Maritime Tropical over the Atlantic and Caribbean. In between them is what's called a polar front, which we are going to talk about a little later on. Each one of these masses of air has a different property. Maritime Tropical is moist because it's over an ocean, and it's warm because it's tropical, and the rest are similarly described. Moisture can be added or removed as they move across the land and the ocean, or the temperature can be increased or decreased. These masses of air form high and low pressure systems. Now, a high pressure is characterized by stable air. You just learned what stable air was like. Sinking air with surface divergence, and we're going to see that in a minute. Light winds that increase with distance from the center. And those of you who are sailors who've gone sailing during a time of high pressure, been out in the middle of the lake with no wind, know what this feels like. Weather is clear to partly cloudy, no precipitation, wind around the edges of the high pressure. Lovely weather. Clear skies at night can produce the dew, frost, or fog, as Bob talked about in the previous chapter. Low pressure systems are characterized by unstable rising air, surface convergence, and upper atmosphere divergence. Strong gusty winds increase closer to the center because we're converging. Again, unsettled cloudy weather. The clouds are forming because the air column is rising, often with precipitation, rain, showers, thunderstorms, hurricanes. A hurricane is a really tight, low pressure system. Highs and lows are steered by the upper atmosphere winds at 18,000 feet or 500 millibars. That's what we talked about Tuesday, if you'll remember. That's why weather forecasters look at the 500 millibar chart, because up there are where the air currents that are steering the highs and lows are. Divergence or convergence aloft affects the highs and the lows. I'm just going to briefly touch on this. It's much clearer when we see the picture. Divergence aloft causes rising air forming and deepening the low. Convergence aloft causes falling air forming and strengthening the high. Temperature advection aloft also affects the highs and lows. As the wind pattern aloft moves, the highs and lows move with it. And here's the picture. What is happening? Now, this isn't a, these aren't moving in a horizontal plane. These are rising up and then plunging down into the top of high. It's converging. Air is coming in from all directions to the top of this high pressure and then spiraling down. And when it gets to the bottom, it spreads out. It diverges down at the bottom. If you will, think of a bucket of water being spilled onto a floor. It goes straight down and splash, spans out. That's the divergence they're talking about. Over on the other side, we have a low pressure zone. Here we have air being drawn in, converging on the bottom of the low where it begins to spiral up. And then when it gets to the top, it diverges. It mushrooms out the top and spreads out. And that's what they're talking about when they talk about convergence and divergent winds, air being drawn in or blown out. Okay, that's what's happening with highs and lows. Now, fronts and storm systems. The types and symbols and characteristics of fronts, the types of storm systems, their structures and characteristics, cloud types that happen around them, and their movements. Okay, a front is the boundary between different air masses. And the reason it's called a front is because the first serious scientific weather forecasters in America in the 19th century were all soldiers in the Civil War. And they thought about the weather as warfare and fronts between armies. There are 4 different types of fronts based on which air mass is advancing. A cold front is where a cold mass of air is pushing under a mass of warm air. A warm front is where the warm air is riding up over a mass of cool air. Stationary fronts are where 2 air masses are pressed together and aren't moving really in either direction. And an occluded front is where a colder body of water, of air rather, is overtaking a warm mass of air, and you end up with 3 types of air pressed together. We're going to see that in a minute. This is what the symbols look like. A cold front has little pointy items on it. That they have a name, I forget what it is. Pips. A warm front has semicircular pips on it. Stationary front has both on alternate sides, and an occluded front has both on the same side. So here's a cold front. This is actually not a section view, it's kind of an isometric view. And you see here is a bubble of cold air. Here's the front. This cold air is moving from left to right, and it's pushing under the warm air, because the warm air, of course, is lighter. It tends to rise. As it rises, it cools. It can hold less and less moisture. It gets close to the dew point. We get condensation or clouds. You get more condensation, you get precipitation. So as the cold air pushes under the warm, moist air, it's pushed up, cools, and forms clouds and precipitation. A warm front, you've got a mass of warm air sliding up, if you will, the backside of a mass of cool air. Same thing is going on, just in a different pattern. The warm air is being pushed upwards on this slope. As it rises, it is cooled. The dew point, or the relative humidity goes up. It forms clouds and precipitation, but it takes a longer time. I believe in the book it shows this as being several hundred miles, whereas the cold front is like 100 miles or so. Oh, here we are. You see here's the approximate distance in nautical miles is just like a couple hundred. Whoop, there it is. Like 200 miles is where all the weather is in a cold front. Whereas in the warm front, it extends 500 or 600 miles. Way in front of the front itself, you've got cirrus clouds, then cirrostratus clouds, altostratus clouds in the warm air mass, and nimbostratus clouds. Warm front have stratus clouds in them. Those are the flat sheet type clouds. Whereas in the cold front, you'll have cumulus type clouds or cumulating clouds, altocumulus, regular cumulus, and right at the front itself, where the air is being pushed up sharply and cooling rapidly, you'll have cumulonimbus clouds or thunderstorms. You get more and more violent weather on a cold front because it's being pushed up more sharply and it's being pushed up higher. Alrighty. A stationary front, it's remains nearly the same place just because the air is not pushing so hard. So you've got clouds, not so much precipitation, just again because there's warm air and it is being pushed up, but not as forcefully as it would be if this cold air mass was advancing strongly. So there's a lot of clouds, maybe some precipitation, but otherwise not much or nothing is going on. An occluded front, it's kind of rare, but you've got a cool air mass pushing under a warm air mass up against a cold air mass. So you've got warm air lifted off the ground by two cooler air masses. I didn't want that one yet. So the top figure is a warm occlusion, the bottom one is a cold inclusion. The difference being the temperature of the air mass that is pushing into it. But in both cases, you've got a body of warm air pushed up above the ground. Now here is our weather. A low pressure center with two fronts. There's a warm front leading and a cold front behind it. Cold air is coming down behind, pushing this front. Warm air is coming up from the south, pushing this front. In the mid-latitudes, they're more properly called extratropical cyclones to distinguish them from hurricanes. This is what we get through here every few days, summer and winter. Now you'll notice we talked about the wind and the Coriolis effect. The winds are entering here on the face of the warm front, then going around the low pressure center, counterclockwise due to Coriolis. Because of friction and movement of the air mass and other things, they aren't following exactly the isobars. They're curling in slightly. Here in the warm sector, we've got, again, isobars and warm winds that are crossing the isobars at a slight angle. Now, watch what happens. These things move from southwest to northeast, usually. Not always. We're going to look at storm tracks in a minute. Now, if the low is passing to the south of the observer, the wind's back. Now, this isn't a really good picture. It shows this dude standing here. You have to imagine a person standing on this line, facing into the wind, facing to the low, down to the right. Now, the low pressure is to his left and a little behind him, just like the Bice ballot rule says. The low moves.
You mean to his right, yeah?
Yeah. I did say, did I say to the left? I
You said
should have
left.
said to the right. You're absolutely right, Bob. Thanks for catching that. Okay, now imagine he is standing where that little caricature is, but he's going to be facing directly to the right, into the wind. Again, the low is going to be to his right and maybe a little behind him. Once more, now he would be facing towards the top of the page. Again, the low is going to be to his right and slightly behind him. Everybody see that? As the low goes by him, the winds change from coming out of the southeast, out of the east, and then out of the north. So they're veering, or they are backing. Yeah, I get that confused too. The winds are backing. The apparent direction of wind changes in a counterclockwise direction. Now, here again, the low is going to pass north of our little friend here, friendly neighborhood weather observer. Here, again, he's going to be facing south and a little east of south, and the low is going to be behind him to the right. Here he is in the warm sector. The wind is coming from the southwest, and the low is behind him and to his right. And here he's going to be facing again north after the passage of the cold front, and the low is again to his right. So if the low is passing to the north of the observer, the winds are veering, changing from southeast to southwest to northwest. So that's, you always have to remember when you're standing facing into the wind is being caused by a low pressure zone. It's going to be to your right. This is very useful if you're on Key West and there's a hurricane coming. Which reminds me, briefly, I don't know how many of you are familiar with this. This is an excellent book, Isaac Storm by Eric Larson. It talks about the genesis of hurricanes, what hurricanes can do, and how weathermen in the 19th century looked at weather and thought about it. It is scary, it is very well written, and it is very educational. So if you are looking for a good read, Isaac's Storm. It came out in 1995, just before the 100th anniversary of the Galveston hurricane. Okay, onwards, the formation of lows, cyclogenesis. Now there are two theories about how cyclones form. One says that a little kink in the wave of the polar front forms a low, and the more modern theory is that upper level air converging and diverging due to the polar jet stream causes the front to form a low. So you see here, you've got a polar front. It starts straight. A little kink develops in it. The kink bends even more and the wind begins to circulate around it and form the low. Whoop. And here's this picture again. The modern theory is that the disturbances aloft cause air to converge at the top and then spiral down to form a high, or to begin drifting apart, which causes a lowering of pressure, and the air begins to rise and is drawn in at the base and spirals upwards and out. Bob can probably talk to me about this more than I can, but I see these storm tracks here, and they're forming like way out here in the Pacific, which is nowhere near the polar front, so I don't see where that could have anything to do with it. I'll talk to Bob about that sometime. He can pummel me for it.
Which is that? What was your
I'm joking. I'm joking, Bob. I'm saying
okay.
that the book here is saying that lows form as kinks in the polar front, but like out here, the lows starting in the middle of the Pacific are nowhere near the polar front. So I'm sure there's some other reason for lows to start. I know that they start in off Africa just because of winds coming off the desert, hitting the ocean and beginning to rise and form a circulation.
This is referring, it calls them cyclones, but it's referring to extratropical cyclones. So it should
Yes,
probably say that if that isn't clear.
Right, you're absolutely correct in that regard also, that these are forming not because they're hurricanes or becoming hurricanes, though that's really neat to watch, but just an area of the atmosphere begins to rise and draws air in from around it, and that forms a spiral circulation. Now, cold and warm core lows. Okay, if the center of a low pressure area is warm, the lower density decreases with height, and the lines of equal pressure just kind of sink a little bit. A cold low, you get a much greater change in the precipitation. Whoop, quit that. In the change in pressure at the center of the low. Now, to summarize, air masses are pools of air with similar characteristics: warm, cool, wet, dry. Source regions are determined, the source region and the, would you stop that? I'm using a touchpad, and if you touch it too hard, it advances whether you want it to or not. So I apologize for that.
You have a back arrow? Can you use the back arrow?
Oh yeah, I did use the back arrow. Not hard enough. Okay, they are, these different masses of air are modified as they move over new areas. A maritime polar one will warm up and become a continental tropical one. Or maybe not tropical, but it will increase its moisture content and warmth. Adding or subtracting moisture, heating or cooling. A front is where two air masses meet. Cold front is cold air pushing under warm air, warm front, warm air sliding over cool air, stationary front, little movement, and occluded front is a cold front overtaking a warm front, overtaking a coolish front. High pressure areas are air masses with anticyclonic rotation. They rotate clockwise. Low pressure systems are extratropical cyclones. They are rotating anti-clockwise. Fronts tend to trail out to the south of low pressure zones. Pressure systems are steered by the upper level winds. If a low passes south of you, the wind backs. If a low passes north of you, the wind will veer. Lows formed by cyclogenesis, diverging aloft, lowering the surface pressure, or circulating, develop, forming a wave in the polar front. And that's all I've got. You want me to take these questions, Bob? Or are you going to take questions?
I think for the purposes of times, we'll just do the questions in the book there.
Roger. Okay, I am stopping sharing. There you go.
Good. Before we go, any questions for Chaz at this point? Any questions?
I was just wondering what the significance of the colors were in that last chart where all the cyclones were moving in, you know, different colors, what they were for. Anything?
Chaz?
That was trying to describe the difference between a low pressure with a warm center to it and a low pressure with a cool center to it. The book does discuss this at greater length and a little clearer, I think, than that slide does. but it's that if
I didn't
the
understand it in the book either. I was hoping to ask here
If-
and figure it out.
if the center of a low is warm, there isn't as much change in the atmospheric pressure in that low as there is if it has a cold center.
Gotcha.
What
Okay,
it's
cool.
trying
Thanks.
to get across.
All right.
So
Thanks.
it's, yeah, the pressure in the low is what it is. You can just read it with a thermometer and you know.
I think we see my meteorology shirt.
Hey,
All
nice
right.
shirt there, Bob.
Thank you.
Thank you,
Yes,
thank you.
it's an heirloom, 1986. Great job, Chaz. All right, we're going to try to do speed and try to get you guys out of here on time today with the questions. I'm going to go down my list. Adam, number 1, in highs, the
In highs, C, air spirals out of the center.
correct. Alejandro, in lows, the
Air spirals into the center.
correct. A, that's good. Alex Carmichael, I can't remember who was driving. Is that you? Normally, our air masses travel across the U.S. Number 3.
Okay. It would be B, faster in the winter than the summer.
Excellent. Amanda McAllister, number 4, precipitation ahead of the warm front is usually
Long in duration and steady.
correct. Number 5, Anita Lutkus, precipitation ahead of a cold front is usually you there, Anita?
Unmute. Okay.
Number 5.
Alpha, short in duration and showery.
A is correct. Well done. Ann Brink, number 6, when a cold front passes, the wind you there? Ann Brink.
Oh, there we go. Now I'm unmuted.
Number 6.
Number 6. I'm going to say A, veer sharply.
Well, remember it comes out of the south, and then like a clock, it goes backwards, right?
It goes backwards. It'd be C, reverses.
Well, actually, they're looking for backs sharply. So after a cold front passes, the wind backs. So go ahead and look at your material, see if you can find the answer to this. Number 7, Arcia. As a cold front passes, the winds are?
Strong and gusty, B.
Well done, correct. Bill Vahey, number 8, conditions after a cold front are usually?
Good visibility with cumulus clouds.
C is in Charlie. You are correct. Well done, Bill. Chris Strawman, number 9, in the occluded portion of a cyclone, the warm air.
C, Charlie, is held aloft.
Correct. Don Broughton, can you answer? Are you the one who's driving? Can't remember. Who was it? Was it you, Don?
Oh, that's not me.
All right, Don, number 10. An occluded front is formed when?
Fast cold front overtakes the warm front, B.
Well done. Deb Salvi, number 11, north of a low.
D, all of the above.
All the above. Wait a second. Yes, all the above. Next one is Gary Cahill. The polar front forms storm systems because... You there, Gary? Gary, can you hear me? Harold Schlahan. The polar front forms storm systems because?
D, prevailing westerlies and polar opposes each other.
The easterlies, good. Jane Bickle, number 13, the jet stream is?
C, a high altitude wind.
Excellent. Jason Pfeffer, you said you were driving, right? Or are you done driving? You still driving, Jason?
I'm done driving.
Can you
I'm
see
done
that?
driving.
Okay, can you do number 14 for us, Cloud? And in area 1 are typically?
D, stratiform.
Correct. Well done. Jeff Silberg, number 15. Clouds in area 5 are typically?
Alpha.
Cumuliform, correct. Jessica McAllister, 17. Oh, no, I'm sorry, 16. Clouds in Area 3 are typically, or no, I just did that one, didn't I?
No.
All right, Jessica, number 16.
Typically cumuliform.
Good. Number, Jim Davey, number 17. The front next to 7 is a?
A, cold front.
Cold front, correct. Number 18, John Puskar, the front next to 6 is a? You there, John?
Oops, sorry, cold front.
No.
Number 6.
Number
Remember
6
this?
or 17?
We're doing 18. 18, John.
18. It's warm front, bravo.
Warm front is correct, good. John Vondra, I don't think John's here tonight, is he? John, are you here?
Yep, I'm here.
19, the wind has veered to the northwest. The thunderstorms are over and the barometer is rising rapidly. Where are you? In your basement. Did you stay in your basement?
Yeah, number 5. Charlie.
5, and here I am talking and not paying attention. 5 is
Charlie.
correct, good. Good job, John. Kevin Worthy, it is now colder. The wind is northwesterly. The sky is clear or partly cloudy. Where are you on this map?
D Delta, number 3.
Correct. Good job, Kevin. Larry Lindbergh, number 21. The winds have been backing most of the day. Where are you?
Charlie, 4.
Over here. Yeah, way to the north because the winds are backing. Correct. Yep. Next question, number 22, is for Brian Hinton. Sorry I didn't pick on you earlier, Brian. A mid-latitude cyclone like this one will typically move in the direction from?
A, 5 to 1.
Correct. A is correct. Good job, Brian. Linda Coppell, number 23. Divergence aloft can be caused by?
A. Ooh. Yeah.
Good. The wind, yeah.
The wind's speeding up with distance.
Good. This is a tough one. Good job, Linda. Mario, number 24. Divergence aloft encourages cyclone formation because it? You got this one, Mario? You there, Mario? You there, Mario? Can you unmute? Can you hear me, Mario? Mark Frankel, 24. Divergence aloft encourages cyclone formation because it?
Because it supports surface convergence.
Excellent. Well done. 25. This is for Mark Hazem. The paths of cyclones across the U.S. are determined by Hazem?
The steering winds at above 18,000 feet.
Very good. Mike Haley, 26. Cyclones can form?
Cyclones can form over the Gulf, over the Pacific Ocean, over the Great Plains, all of the above.
Very good. Mike Zendrick, number 27. The symbol for a cold front is aligned with?
B, triangles.
Triangles, right. Good. Nick Nita, number 28. The symbol for an occluded front is a line with?
Triangles and semicircles.
D is correct. Good job, Nick. Patrick Dugan, 29. The symbol for a stationary front is aligned with?
C, triangles and semicircles on different sides.
C is correct. Good job. Patrick Leonardi, 30. The symbol for a warm front is aligned with?
Semicircles.
Correct. Good job. Paul Luna, number 31. A CP air mass moving through the Midwest will?
Both B and C, D.
The correct answer is D. You remember what CP stands for?
Continental Polar.
Continental Polar, well done. Paula Wicks, number 32. An MT air mass moving up the east coast will?
C, both A and B.
Both A and B. Good. Well done, Paula. Penny Ross, 33. A cold core low does what as the altitude increases? Chaz hit this pretty good. Are you there still, Penny? Did I lose you, Penny? Pete Lemire, 33. A cold core low does what as the altitude increases?
B, deepens.
Yeah, deepens. Bombogenesis. You know, they call them nor'easters there sometimes, I think. Good job. Phil Leonard, 34. A warm core low does what as the altitude increases?
A, fills.
Fills. That's right. That's the last number for 34. It is a little late, so not too bad. Any questions for me or Chaz right now?
Hey, if you're gonna have a T-shirt contest, I could have one too.
I have a question. It's Anita Lutkus.
Hey, Anita, everybody, if you want to turn on your cameras, we're kind of winding things down here. If you want to turn your mics on or your cameras on, as long as nobody's honking too many horns. Anybody mind if I take your picture? You guys look good. I want to take your picture.
I would like to ask a question, if I may.
Yes, go ahead, Anita. I'm sorry. Go ahead.
I'm having a real hard time with the diagram regarding the different types of clouds and the different locations of the winds and where you're supposed to be.
Can you hear me?
Can you hear me?
Yeah, I can hear you, Anita. Somebody else jumped in. Did somebody else want to share something with Anita so we can let her finish? Go ahead, Anita.
And that little figure, I can't tell if the figure is facing towards me or away from me, that little black person. And I don't know whether this warm air, cool air, warm front, cold. I mean, I understand the warm front, cold front. I get that with those little tips, as you call them. But am I looking down at that picture, or am I looking horizontally at it? I just am totally lost about all of those questions.
You are looking directly down on a cold. I'm sorry, you're looking, Anita, you're looking directly down on a low pressure system with two fronts trailing down to the south from it. The warm front is trailing to the southeast and the cold front is trailing down to the southwest. The
So
air is rotating around the L.
View. It's an aerial view is what you're telling me?
Yes.
I'm looking to, but that little person, I'm not looking at the top of his head.
That's a lousy diagram.
It's a lousy diagram.
That's a lousy piece of art. It should be like you should be looking down at the top of his head and he should be turning. That's what I was trying to describe as I was talking about that, was which way he would actually be standing.
Yeah, because I know that
that picture, the man is lousy.
If he sticks his right arm out and he faces the wind and the low is behind him to his right, yeah. But it's like I'm totally, I'll miss every single one of those questions on the exam, I know.
Just always remember, when the wind is in your face, you stick your right arm out.
Yeah, I got that.
Okay.
I got that
so,
part.
and you know what, Anita? I wish I could disagree. This is the first time we used the 2018 slides. The late Amy Seeley, who is a huge friend of ours, passed away not that long ago. I'm sure she had absolutely nothing to do with those slides because I didn't think they were good at all. But I agree with you, Anita. Not good slides. Very difficult to tell what's going on there.
So it's
again,
not just me. I'm not alone.
No, it's not just you. I think everybody would agree. Chaz was saying that it's really hard to tell what's going on there. And I was like, when I was looking, I was like, Amy had nothing to do with these slides because these are terrible. And she was wonderful. For anybody that wants to, go ahead, Chaz.
Imagine that you're looking down on Bob Allen's bald head as he's facing into the wind, and you will then see that the low is always to his right and behind him.
Okay,
Or
thank
you
you.
can look at my bald head. It's not as bald as Bob's is, but you can bounce radar signals off of it.
It's
But
no
no,
reflection
don't look.
on the instructors. You guys did a great job. It's picture I'm having a trouble with. Okay, thank you.
Thanks for the question, and anybody that needs to go, it's for some of you, it's very late at night. Thank you so much for being here. We're going to stay for a few more questions. You are all welcome to stay, but if you got to bounce, don't feel bad about it. Yeah, thanks everybody that came here tonight. Next question. Anybody else got a question? You're welcome, Hassan. Mark, how you doing? Oh, who was that? Mark Frankel, I couldn't hear you. Oh, you have the problems with the microphone. You can nod.
I don't have any problems.
Oh, okay. Did I try to call you? Somebody I tried to call them and they couldn't answer.
Not me.
Let's see. I got two different screens going on here. John Vondra, how are you tonight? Are you doing okay?
Good, thank you. I have a little problems at the beginning, but I had to come in and go out, one with the Windows and then one with the iOS. So it took me a little bit, but I'm doing fine.
Oh,
very good class, guys.
Thanks. Well, we're glad you're here. Who else? Mike Haley, how are you tonight?
I'm great. How are you doing?
Good. And you're a vessel examiner too, aren't you?
Well, I'm in arrears on just about everything I used to be, but yeah.
Good. What do you got on your shirt, Ron? Are you getting in the T-shirt contest too with the shirt? I don't think mine can beat you. I don't know if you could all see. One of my classmates put together this T-shirt, and Chaz was showing the front. I don't know how well you can see this there, but there's a cold front and a warm front, and that's from back in 1986 when I was in school there with our friend Rich DeMaio there, or Rick DeMaio, who went on to fame and fortune as I continued in my office job, not doing television.
You know, Bob, that people might be confused because, you know, they might think that you went to another school in Wisconsin, which would be River Falls, which is known as MooU because of their husbandry sciences for cows.
Well, you know, I met a girl from River Falls in UW-Madison, Jennifer Richardson. That's another story. Linda, how we doing? Can you hear me, Linda? You don't want to turn on your camera? You there, Linda? I don't blame you. Sean Landa, how you doing tonight?
Oh, I'm not muted. I'm good.
Good. Now, is this your first AUX class, or did I ask you that question already, Sean?
No, this should be my last AUX class.
Going for the device.
It's only taken 25 years.
No, that's cool. Rocking that bling. Now, were you in flotilla? You were in 10 at one time, weren't you?
No, I was in 8, 6, and then 4 now. I'm an aviator, or was.
Yeah, you remember when I used to be in 8, don't you?
Oh. I do. We've been around a long time, Bob.
Back when I had that old Piper Apache, that thing was awesome.
Oh, I forgot that was yours.
Yeah. Yeah, we did that trip up to Madeline Island. You remember I was trying to get everybody to do the trip to Madeline Island. I don't know if you were in the flotilla then. To set up that temporary radio outlet. You remember that?
Yeah, and then then Barry had the 310N. We did some ice flights in that. And I had a Piper Warrior at the time.
Was that at Pewaukee, or where did you have that airplane at?
It was at Pewaukee because I lived in Northbrook at the time, and I went to Lewis University, so that's how I commuted every day.
Mm-hmm. Oh, who was the police officer? Remember, he couldn't come to the meetings because they changed the rules, and he couldn't wear his weapon anymore to the meetings.
That was recently, wasn't it?
No, this is a different guy, way back in the day, and he had he had another 140 and it sat on the ramp, and he couldn't afford to fix it anymore because financial problems, and that was up at Pewaukee. That's a long time ago.
I don't remember that. Didn't Barry wind up with a 180 or something?
Was it a 170 or 180?
It was a 180.
Yeah, our friend Barry Danis, a longtime Flotilla 8 member, he had an airplane that was a very old design. It was a tail dragger, and he was a very skilled. He was a flight instructor, and he could fly it like this, so that if the wind was in his face, he could hover just like a helicopter. Remember? Did you ever get a ride with him in his plane?
Not the 170.
It was a 170.
It was a 180.
Harold,
yeah, it was
go ahead, Harold.
Yeah, it was 180. I flew with him a number of times doing operations out of Pewaukee there. He was a good guy.
Yeah, he's down in Florida now somewhere. You know, he lives near where Jack lived before he passed away. How are you, Ron? Are we getting the good information for you? The diagrams, I agree with Anita. That diagram was very poor. What do you think, Ron?
I think that watching the Weather Channel does not make me a weather expert. There's quite a bit to learn. I'm really enjoying it. It's a lot of work. I've spent time going over the course material before coming on, and listening to everything is helping to solidify it. So thank you very much.
Harold, when you hear what I shared, this photo here, this is from when I rode on your sailboat. You remember that?
Yeah, it was a beautiful day.
Yeah, good times. Chaz, anything else you want to share?
Does Chaz have a boat?
Yeah. Yo, I got two of them, one for each foot. A 20-foot Balboa and a little 12-foot O'Day. So I didn't sail them at all last year though, so I got to do some more sailing.
Absolutely, good for the soul.
Mm-hmm. Although even if you don't sail them, they're fun to tinker with. But I keep the O'Day around because it's so easy to set up, and I can take it out here to the little lake and sail it fast. The Balboa is bigger and more stable, but it's like 45 minutes to set it up. Yeah, I don't, getting back to your first question, Bob, I don't really have anything additional to add.
You know, I've got a Sea Snark, right? That's your O'Day is a 12-footer?
Yeah. So
yeah, my Sea Snark's an 11-footer. We should go have races. We'll have a regatta.
We could do that. Okay, here is a sort of a sea story. One of the last times I had the O'Day out on Bussy Lake, about 3 years ago now, it was a nice, clear day, cumulus clouds, things were fine, winds were kind of light, and just as I was heading in, all of a sudden the wind veered and picked up to like 12 or 15 knots. And it was a clear front. You know, no indication of any change of weather at all, but the wind changed decisively. And I had a dickens of a time getting back to the dock with it.
Now, Paula, did you do some sailing, or are you more of a power boater, Paula?
I'm not a boater.
No? Okay. Now, you're in 10 or you in 4? I'm trying to remember.
4.
4. Now, I guess Bill's fighting a cold or something. Did you hear that already or no? Well, you didn't hear it from me, but he's sick. What's that?
Bill Russell, you mean?
Yeah, he was here
I had
Tuesday.
not heard that.
What, you did?
I did not hear that. He was at our meeting last night.
Oh, was he? Well, I was told on Tuesday that he was recording this, but he wasn't feeling well, and that's why he didn't answer my questions when I asked him. Maybe he was probably doing something else. Who knows? I'm recording this for Stafford, but I've stopped recording so I can talk about him now.
Well, I'm going to sign off.
Bill, are you a sailor too? Do you have a sailboat?
Which Bill?
You, Bill. There's no other Bill.
No, I don't have any. I don't have any boats. I'm an electronics guy.
Yeah, now you know Mike Veneer then, huh?
Yeah, that's who I came into the auxiliary with.
Yeah, he was doing publications for a while, and now he's doing communications, I think.
Yeah, well, I first met Mike at a radio club meeting many years ago, and it was about the time that, in my case, I wanted to do something different. I kind of had hoped that I could do more with the auxiliary, but with my advancing age and other issues, I don't think I'm a good candidate to go out on a boat. Not, you know, it's one of those things where if you have certain limitations, that's fine until you come up with an emergency situation where you need those resources that maybe you don't have.
You know, I think I said Madeline Island. It was Beaver Island. Harold, did you go with us to Beaver Island? Did you fly up there during the Chicago to Mackinac race?
Yes, that was to Beaver Island. And boats have a lot of electronics, and so do airplanes. So I'm sure you have a lot of electronics to work on.
Well, no, the problem is, what I worry about is if you come across an emergency scene, to be specific, my specific problem is I'm deaf in my right ear. Now, I've been deaf since age 7, so I've had to live with this for a long time. And I can tell you that when you have a person that can't hear out of one ear, when the sound gets over to that bad side, you cannot tell the direction the sound is coming from. And sometimes that could be critical, you know, if you're on a boat where the person that needs to communicate with you, he's on your bad side, and you've got a bunch of noise on the left. So I kind of think at this point in time, my ideas about getting out on the water are probably not such a good thing.
So what I was talking to Harold about is 1 year during must have been 2006, huh? What was that guy's name? He just got out of the military and he knew a lot about radios. And we set up a portable radio on Beaver Island so that we could monitor in case any ships were having an emergency. You could have done that. I mean, Barney Zaffron with us, and I think he was 92 at the time. But he wasn't going to get out and do operations, but he could sit and listen to the radio with us.
Yep, I can do that too. That's the thing with the radio. It's a point source. It's in front of you, so you don't have to worry about where the direction of the sound is coming from. It's pretty straightforward.
We were monitoring the Mackinac race, which has 300 boats in it normally from Chicago to Mackinac. And sometimes it's hard to keep track of them, but if one or two or a number of them get hit by some strong weather, there could be, you know, potentially a lot of problems. So asset, you know, such as yourself, you know, monitoring the frequency and tracking some of the boats would really help.
Yeah, that's true. I can see where that would be useful. And right now, some of the things that I do are HF radio nets, which we've just started back up about a year or so ago, and that's taken up a lot of time too. And we're kind of stuck with radio propagation at this time of the sunspot cycle. Creates a lot of problems for long distance communication. Like we have a District 9 net, and we wind up communicating through guys on the East Coast because of the skip. We skip over the guys that we need to talk to close, and the guys on the East Coast relay back. It's interesting.
So what's this, Paul? You the new Vice Flotilla Commander?
That's what they call me.
Congratulations.
Well, thank you.
You guys got any PE classes going right now, or because it's all, are you doing them in person or is it virtual, or?
I'm not sure yet what's going on. We have to get some reports in, see what's happening. Everyone's making plans for this and that, so we'll see.
Good, yeah. Well, Cook County, I think they're pretty much active on their issuing of the COVID shots. I don't know if that's something that we talked about already. Not sure you're.
I can't seem to get one. It's really frustrating.
Somebody said if you're really good on computers, you can find ways to register for them.
Well, they don't seem to have us slots open, so they say call back tomorrow.
Well, there are different places. You know, Chaz might know a lot about the city. Who knows a lot about Cook County and where you can get a shot? Anybody?
They have 8 centers, and clearly they're very busy. One of them, Arlington Heights, is nearest here, and it's you would think they weren't even open. So it's really frustrating. But Cook County has determined they're not going to let everybody come in until they get through all of us who are over 65. So hopefully, I did have friends who were able to log into Walgreens at 5 o'clock in the morning and get a slot 2 weeks out.
For that day? Was the shot for that day?
No, it was for 2 weeks later. I mean, it's not great. So we just keep plugging away at it. We'll find it.
Yeah, well, tomorrow afternoon, Harold, I'm going to be flying the twin-engine plane. That'll be exciting. Hope the weather cooperates.
Yeah, I was looking at that plume at work today, and it kind of meanders a little bit. I don't know if any of you have driven under the Lake Michigan plume that sets up in the winter sometimes, but it can be close to a quarter-mile visibility while you're in it, and you can break out of it, and it'll be bright and sunny day. But the people who are underneath usually accumulate a lot of snow, which is fascinating. All the weather forecasters say it's pretty hard to forecast snow, you know, with a lot of degree of certainty.
The plume you're talking about, do they ever show pictures of it on the weather or something that you could see it?
They do. Tom Skilling usually talks about it, and Mike Kaplan and all the other major forecasters, because it is very localized sometimes. And you could get a lot of snow if you're underneath it, and it kind of sits there and comes down Lake Michigan and picks up more moisture and then drops it on the cold surface underneath. Usually Indiana usually gets a lot of that because they're the full fetch.
Oh, right.
Know.
It hits land and dumps on them.
I had an experience in Michigan where we were going up to Mackinac Island, and I'm rolling about 70 and not paying too much attention, and all of a sudden the highway is just covered with snow. It like went from a wet pavement to snow instantly. I'm like, oh boy, you know, you back out of the gas and hold on till you get your speed down to make sure you're not going to go off the road. But that happened twice on that section of the road. You know, it was a narrow band and came out of nowhere and then was gone, but came back again. You're muted, Bob.
So I was talking to the Commodore today about D-Train in March next month. Obviously this is going to be all online, but he was saying hopefully by October things will be under control, and maybe we could have a D-Train, or maybe some people could watch it online and some people could attend in person. I don't know. I'm hopeful. You know, I'm hopeful that we can get that opportunity. But it was exciting to talk to Harvey Randall today, the big boss. He's up there in Milwaukee. It seems like every other year we get either a Commodore from Chicago or one from Milwaukee, and they kind of switch off every 2 years. And we did have somebody from Indiana one year, or was it Southwest Michigan? I'm trying to remember who that was. But other than that, it seems to rotate between Chicago and Indiana. Jim, are you doing, are you a district staff officer? What are you doing this year?
I was the VE staff officer up until just this past year, but right now I'm just handling materials.
For the district?
No, just for flotilla.
Oh. Yeah, there's been some turnover, some new people coming in there, and some openings. I don't know if you all saw that note about now hiring. They're looking for more volunteers at the district level, so who knows what will happen there. I told them I'd do member training. I have a little experience, but sometimes, you know, when they don't pick it, it's a lucky break. So we'll see. We'll see if I get selected or not. Mike, are you the flotilla commander this year?
No, I'm not.
Who's your?
I'm basically my big deal this year. I'm doing the Sea Scout thing, so I'm currently in a Sea Badge course. I sail as well. I've got a 35-foot Pearson, so I kind of want to take that and bring it to all what they call ships, which are troops, I guess. And I want to, you know, make that available to all the ships in the Chicago area. There's even one out in Michigan City. So Jeff Bailey and I are working toward that goal for this summer, actually.
It's a newer program, and we have one of our guys, John Hendelli. I don't know if you know John, but he used to do boating.
Not yet.
You know John?
Not yet.
Okay, but I just appointed him our new auxiliary scouting person, flotilla staff officer. Now, as far as I know, there's no liaison to Columbia Yacht Club ship.
Well, that's what we're going to try and work on. We're going to try.
Is that you, or you're just checking out all the ships?
We're just starting this. I mean, just starting. So we're going to try and contact all the ships and make that Pearson available to them. Supposedly, Jeff Bailey has already contacted them, and he says that everybody shows great interest. So because they don't have anything like that. So, you know, hopefully we can just keep moving along like that.
Plainfield has a fairly active ship for their scout group.
Well, we know there's one in Tinley Park. We know there's a couple in the Chicago area, the Yacht Club. All right. And then there's also one in Michigan City. I'm not familiar with the Plainfield one. I think this is the first time I've heard about that. However, you know, whatever it is, they can all, you know, they'll all be able to come out on Lake Michigan on a larger vessel and learn how to sail. And that's the big deal, you know.
I don't know how many of you heard about this, but they're talking about allowing Sea Scouts who are 14 years of age and older to join the Coast Guard Auxiliary.
Oh, absolutely. And why not?
Yeah, you already heard that, Jim?
Is it 14 or is it 17? I think you have to be 17 to be crew or coxswain, though.
Read the new read the new letter. 14.
But I mean, you can join at 14, but to become Coast Guard crew or coxswain, I believe you have to be 17 or older. Okay, but you can join at 14, yeah.
So do you know Jay Samstag? Do you know Jay pretty well or not really?
Not yet.
Jay's a flotilla member of 12, and you're an 11.
Okay.
I'm surprised you didn't meet. But
I just transferred.
Okay. Well, he had a Cal 28 down there at DuSable.
Okay. I was at DuSable for 9 years, and to tell you the truth, at $6,000 a year, I'm going to Hammond.
So it's his boat was called Seventh Heaven. If you remember seeing that 28-foot
I've heard it, yeah.
Yeah. But he is Mario, who's in this class, and I are taking a hard look at that boat. Now he donated it to the nautical charity over there at Crowley's Marina.
Okay.
So, you know, Mario and I have had some discussions about maybe getting involved with that boat. But what is it? What does BOAT stands for? It's bail out another 1,000. Isn't that what it stands for?
Yeah.
So my wife
the two happiest days of your life, you know, is when you first get your boat and the day you sell it. So, you know, that's the way it is. It's just a big hole in the water that you pour money into.
Versus an airplane, which I used to have, which is a hole in the sky you throw money into.
There you go. Hey, you know, boys with toys, it's it costs a little bit, but my big thing was I could never really find a lot of people to go out, you know, during the week. I've been retired since 2010. So I always had the time, but I never had a lot of people to go. But man, it's changing now. You know, everybody's getting older and everybody has a little bit more time. and people like the sea badge thing. So I'm taking the sea badge class last weekend and this weekend, and I'll get that. And then, you know, we're just going to move one step at a time from there and see where it ends up.
So you're in Hammond now?
Right now I'm in Burbank, and I'm going to be putting my boat in Hammond Marina this summer.
Well, you know where Pastor Marina used to be, East Chicago there? Did you know Father Len Husk used to be in the auxiliary? I don't know if he's still auxiliarist. Len Husk?
No.
Oh, okay.
Well, was he up the Calumet River there somewhere?
No, he was there in East Chicago. And he, you know, at the conferences, he used to say, anybody want to go for a sailboat ride? So every summer I would go with him 4 or 5 times. Of course, the last couple of years I haven't gone. And I called him late September. No, it was last summer. And he said, no, he's 81 now, and he doesn't feel comfortable going on the boat without his nephew. So he kind of hasn't been sailing as much as he had been, which is sad.
Mm-hmm.
He said to me, hey, how come you didn't call me last year? But, you know, with everything, my retirement the year before.
Sure.
Yeah,
it's a lot. So, you know, but like I say, now I've got a few people that are interested in here. You know, Josh, he wants to come out and do this thing, and you know, we'll see where it goes.
Josh Zajac?
Yeah, so we're just taking one step at a time, and you know, just see what happens. I can't promise or guarantee too much anything, but you know, one day at a time and one step at a time, and we'll see where it ends up. I have a vision where I'd like it to be, but we'll see if we can get there or not.
That sounds fantastic.
Mm-hmm.
Well, team, great to see you. I might kind of wind things down here. Class went pretty good tonight. Thanks everybody for coming. I recorded the whole thing, so I'll be posting it soon, and I'll send out the link in case you want to watch it again. I don't know, I'm not the expert on the internet Zoom stuff, so the second chapter on Tuesday, I said record to Zoom, and I've never used this before, so it was new to me, and that's up there in cyberspace somewhere. I have no idea where it is. But I got a link, and the only thing the link gave me was the chat portion, which is, you know, that doesn't add a lot of value. I wanted to have, you know, the chapter 2, so. Good. Anything else?
Thank you very much for today. It was really good.
Paula. Thanks for being here. I hope you're enjoying it.
Good night, everybody.
Good night,
Good
Paula.
night.
Yeah, thanks, Bob.
Well, what helps a lot are those slides that you show, that you know that we can go and follow through there. So I mean, I was following. I had the slides up here on one of my screens while you had your slides up, and you know, you could go back and forth. So if people use that, like you had suggested they do, you know, that would help them a lot too. Okay, I'll talk to you later.
Thanks, Mike. Have a good night, sir.
You too.
See you, Bill.
Hey, guys.
See you, Harold. Good seeing you.
Bye.
See you, Jim.